In the previous video, we explored a pattern for squaring numbers that end in 5. And we noticed that the answers always ended in 25, and that the number that showed up before the 25 was simply the number before the 5 being multiplied by the next higher integer. So 3 times 4 is 12, and that's why this 12 is here. So for 45 squared, you take 4 and multiply by 5, and you get 20, 25. And then for 75 squared, you do 7 times 8, which is 56, and then attach a 25. That's a recap of the shortcut. In this video, we're going to prove the pattern that we were seeing and show algebraically why it works the way it does. If you're like me, you might find tricks and patterns very entertaining. Personally, I like knowing why things work, so developing a proof algebraically helps ease my mind that these tricks are not just magic and that they actually work every time for a good reason. So let's get into it. So what we need to do is design this problem and say that we're going to square some number that ends in 5. So we need to find a way to describe that number without a specific example. So if a number ends in 5, then it is 5 more than a multiple of 10. So the number we want to square can be written as 10n plus 5. So earlier we used the number 235, and I'm just going to use this example to show you what I mean, but it's not part of the proof. So 235 can be expressed as 230 plus 5. And the 230 better written as 10 times 23 plus 5. Now you remember that earlier we were just looking at the digits before the 5, and we were calling that n. So that was 23. And it's the same n that we're going to be using now. So this number, 235, can be expressed as 10 times 23 plus 5, which is in the structure 10n plus 5. The reason we want to do this with a variable is we can't prove by example. So just because it works for 235 squared doesn't mean it's going to work all the time. So we have to do it in general. So here we have 10n plus 5 getting squared. If you recall from algebra that a plus b squared is a squared plus 2ab plus b squared, we can use that to square this binomial. So we square the first term, giving us 100n squared. And then we multiply 10n with 5 and then double. So we get 100n. And then we square the 5, which gives us 25. Now this may seem a little bit forced to prove our point, but the first two terms have a common factor of 100n. So you factor out 100n, leaving you with n plus 1. And then you add on the 25. So that's the result of squaring a number that has the structure 10n plus 5. Now let's see what this result means. So the n times n plus 1 should look familiar. That is the number that's before the 5 getting multiplied by the next higher integer. And then multiplying by 100 makes the numbers shift to the left 2 units, and then it leaves those last 2 digits for the tens place and the units place empty, so that when we add this 25 here at the end, it fills in those spots. So let's see how this works with an example. So if we're trying to square the number 45, if we look at the structure of the number 45, 45 is 10 times 4 plus 5, which shows us that n in this case is 4. So if we try to use it in the structure that we found here, we have that 45 squared is 100 times 4 times 4 plus 1 plus 25. I'm following the pattern that we have here in green and replacing the n with 4. So here we have 100 times 4 times 5, so that's 100 times 20 plus 25, and that is 2000 plus 25. Now, if we hadn't included the 100 in the front, you'd just have 20 plus 5, but we don't want to add the 20 and the 25. We want the 20 to be in front of the 25. That's why the 100 helps the 20 slide 2 units to the left so that the 25 can show up in the tens and units digit, getting us 2025, which is exactly what 45 squared is. Hopefully this example helps you understand the connection between the formula we found here in green and the pattern that we saw when we were investigating at the beginning of this video. Now that you've seen the reason that this works, maybe you can trust the trick a little more, and next time you have to square a number that ends in 5, maybe you won't reach for your calculator right away and instead use this little shortcut. I hope you enjoyed this video. See you next time!